We want to calculate the temperature of the Earth from the solar constant. So the title of this is Temperature of Earth from Solar Constant. I just want to say a little bit about the solar constant in the sense that it's not a true constant like the speed of light is, or Planck's constant, or Boltzmann's constant, or the charge on the electron, or the gravitational constant. And it's not a real high precision number. It's on the poor precision side. Something like the gravitational constant doesn't have a lot of digits associated with it, and neither does capital H, the Hubble constant. And what we'll use is that at the Earth, the power density is 1,370 watts per meter squared. So the word density over here refers to a surface area density, meter squared. So that's the solar constant, and we're going to abbreviate that as SC. We did a talk earlier, an older talk, on which we used the Stefan Boltzmann Law, applied it to the sun to find out what the solar constant was. And so I just want to give a quick review here of what it is that we did. So we're going to say the power emitted per square meter at the sun's surface is P sun sub density. But we're going to start out with just the power density. And we get that from Stefan Boltzmann's law, which is sigma T to the fourth. So the sun's temperature raised to the fourth power multiplied by this constant, the Stefan Boltzmann constant, we can figure out what the power density is for the sun. And we can work that out. And then if we take that power density and so we have we have the Stefan Boltzmann constant here. We're multiplying by the temperature to the fourth power, and we wind up with the sun, the power from the sun density, watts per meter squared. So we can figure out the power from the sun. Now, this power density means every square meter on the sun's surface is emitting this many watts, a tremendous amount of watts, 6.3 roughly times 10 to the 7th watts per every square meter on the sun's surface. So if we multiply the surface area of the sun, 4 pi r squared for the sun, times this power sun density, we'll get the power that the sun is emitting. So if we work that out here, we get this very large number, 3.8 times 10 to the 26 watts is what the sun is emitting, the entire sun. So now let's think of the sun here at the center, and here's the Earth's orbit. So all of this power is falling on this entire large sphere equal to the Earth's orbit. We're trying to get to the solar constant at the Earth. So at the Earth's orbit, the power at the Earth, again in terms of density, will be the power that we calculated for the sun, this large number, divided by, we're going to figure per square meter now on this very large sphere, which has a radius equal to the Earth to sun distance. That is going to be the solar constant. And if we work that out, we get, well, we're going to round it a little bit. We're going to say it's 1,370 watts per square meter. We're going to call that the solar constant, and we're going to abbreviate it SC. So if we come over here, so that's how we came up with the solar constant in a previous video in kind of a quick review. So if we come over here now, we just want to make it clear what we're talking about. Here's the sun, and here's the earth. And what we're talking about, here's 1 square meter that I've kind of lifted off the surface of the earth. And what we're saying is that on every square meter, 1,370 watts are falling. The solar constant. And this is a little bit more of a detailed picture. So out over here is the sun, and what I'm showing, I've color-coded the photons coming from the sun as yellow. They're going to be absorbed by the earth. That will raise the earth to some temperature. Then the earth will radiate, and it will radiate at a lower photon frequency, which I'm showing as red. So yellow is high photon frequency coming from the sun. Red is lower photon frequency emitted by the warm earth. And the earth is nowhere near as warm as the sun, so we're trying to show that. If you look closely, you can see it's longer wavelength as compared to shorter wavelength from the sun. The other thing that this picture is trying to show you is that for a few photons coming in from the sun, in the visible part of the spectrum, there's a lot more photons coming off the earth in the heat spectrum or the IR spectrum. And you know, you'll hear often how important the sun's energy is to life on Earth. Actually, the difference that you're seeing in number of photons here has something to do with entropy. And there are a number of books out there that point out how the entropy plays a very important role to life on Earth. And if you're interested in checking that out further, I would recommend you take a look at this book. It has a small section in it that explains and describes how important entropy is to life on Earth, and that is not really just the energy. Okay, so now getting back to the solar constant, we're going to show the sun here, and here's the earth, and you can see the earth's shadow here. Looks kind of like an ice cream cone here now. So we have the spherical earth, and the spherical earth, the surface area is 4 pi r squared. We're going to calculate the power intercepted by the earth. And to do that, we'll approximate the earth as a flat disk. So we have a disk here oriented orthogonal to the sun. And the flat disk, the area is pi r squared. The surface area is 4 pi r squared, but we're interested now in pi r squared. So the power that's intercepted by the earth is going to be the solar constant that we talked about over here times pi times the radius of the earth squared. Next thing that we have to consider is shown over here. Here's the sun, and we have 100% of the incoming visible light from the sun coming to the earth. The earth is going to reflect from clouds, from the earth's surface, from ice on the polar caps. It's going to reflect 31%. So we have 100% incoming, we have 31% outgoing, and we describe that as an albedo, the reflectance of the earth. So the albedo for the earth, if you look it up, it's roughly 0.31, meaning that 31% is reflected. So if we want to calculate now the power that's absorbed by the earth, it will be 1 minus the albedo times the power intercepted by the earth. So this is what we have coming in. We have 31% going out, so we have a remaining amount, and that's what this gives us, that remaining amount. So this is what is absorbed by the earth. Power intercepted by the earth, we had that over here. So we're just going to take this, and we're putting it in here for power intercepted by the earth. And again, we're using the disk, so it's a pi r squared earth, radius of the earth squared. So this energy, this power comes to the Earth, it warms the Earth comes to some temperature, and then it's emitted as I indicated over here. The energy, some of the power, is emitted by the Earth. And so we use Stefan's Boltzmann's law again. And just as we did in the case with the sun, we'll have that times the spherical area of the Earth. So the power emitted by the Earth is going to be the temperature of the Earth to the fourth power times sigma. That will tell us how many watts every square meter is being emitted by the Earth, and then we multiply by the area so that we have power then. So we have conservation of energy. And we can look at this over some time, so we can look at it as the power being conserved. So we can set these two equal to one another to solve for the temperature of the Earth. So if we do that, we'll have the temperature of the Earth calculated from the solar constant is going to be equal to, it'll be 1 minus the albedo for the Earth times the solar constant. The pi's will cancel out, and the radius of the Earth will cancel out. So in the numerator we just have this, and then in the denominator we'll have the 4 sigma, and then we have to take the fourth root of all of that. So that is our expression for the temperature of the Earth. So if we put in the quantities now, we'll have 1 minus 0.31, 1 minus the albedo, times the solar constant, 1370, divided by, and that's in watts per meter squared, divided by 4 times the Boltzmann constant, which is 5.67 times 10 to the minus 8th. And if I go back here, the units on that are watts per meter squared per Kelvin to the fourth. Watts per meter squared per Kelvin to the fourth. And if we take the fourth root of that, we'll wind up with just Kelvin, and it works out to 254 Kelvin. And that's below zero, so if you convert the Kelvin to centigrade, you're saying that the temperature of the Earth is, in terms of centigrade, will be minus 19 degrees centigrade. So that's well below freezing. And what this shows you is how important gases are in the atmosphere. Because without the CO2 and without water and some other things in the atmosphere, this is what the temperature of the Earth would be. We would be one giant frozen ball. So carbon dioxide in the atmosphere, a little bit of it, is a good thing for life on Earth. And that is why this temperature is low, because we're not taking into account the fact that if we come back over here and look at this figure, we're not, in this calculation that we just did, we're not taking into account the Earth's atmosphere. And what happens is this IR radiation being emitted by the warm Earth is absorbed by the carbon dioxide and the water in the atmosphere. That absorption increases the temperature of the atmosphere, and that is what keeps the Earth at a nice temperature. Now, it's kind of interesting to, so that's how we get the temperature. We set these two equal to one another. Conservation of energy, we're looking at it at a certain time, so we set the powers equal to one another. We solve for the T Earth, and we wound up with 254 Kelvin. It's not too hard to take a look at this, not just for the Earth, but for any planet in our solar system. So in our solar system, each planet will have its own albedo. So for a specific planet, we'll have a certain albedo. And if we come back over to here, we use this expression to get the power density at the Earth. And that was the power emitted by the sun divided by 4 pi over 4 pi r squared. So what we could say is that the power at a planet and this is the density, will be equal to the power of the sun divided by, see, I'm using that as a superscript, divided by 4 pi r squared. And what we would use now here for the r, we could express that in terms of astronomical units. So we could have n astronomical units, and then we would multiply that r by what an astronomical unit is equal to. And I have that indicated over here. It's roughly 1.5 times 10 to the 11th meters. So this would then become the solar constant for a particular planet. If we use the distance that the planet is from the sun. So we could substitute all that back into here, so we would have now the solar constant for the planet. We would have the albedo for the planet. And this expression then would give you the temperature for the planet. Again, this is calculated without the effects of a planet's atmosphere. So if we come over here now, this table shows the temperature for the solar system planets, and I also included the Earth's moon. So here are the objects going from Mercury to the planet Pluto. We're showing the distance from the sun in astronomical units for all the planets. And then we show the albedo. This is the albedo that would be used. The albedo for Pluto is not that well established, although maybe with the New Horizons spacecraft visit, maybe it is. So I'm using an older value. And then these are the calculated temperatures for all the planets. Mercury, Venus, Earth, the Earth's moon, all the way down to Pluto. And you can see that the calculated temperature in all cases is less than the actual temperature. And there's quite a difference for Venus, and that's because of the high concentration of CO2 in the Venus. It's practically all CO2. So that is why the temperature is so high for Venus. The moon is a dark object, so its temperature is, the albedo is a small number, so more of the sun's energy or power is absorbed by the moon. So its temperature is higher than what we calculated for the Earth. And I'm also showing a second value here for the albedo for the Earth. It's 0.37. And so that gives you a even lower temperature if more is reflected. The albedo for the Earth kind of floats between those two values. Mars is particularly interesting. It has a reflectivity, or an albedo, or reflectivity, albedo, very similar to the Moon and to Mercury. And when you calculate the temperature, you get 217, and the typical temperature that you see for Mars is about 218, so they're about the same. And one of the reasons that these work out here so well is that the Mars atmosphere is so thin. Jupiter, there's a difference there. There's actually no surface to stand on Jupiter, so when you talk about the atmosphere, it's a little difficult to really know what you're saying. That's also true for the other gas giants. So there are some issues with these differences between these, the calculated and the actual. It has to do with the atmosphere, with the rotation rate of the particular planet, the eccentricity of the orbit, and I mentioned that Jupiter has no surface. So I just want to summarize and say that we calculated the temperature of the Earth for an albedo of 0.31 to be 254 degrees, to 254 Kelvin, which corresponds to minus 19 degrees centigrade. And again, it's because of gases in the atmosphere, CO2 and water, that we have a much more livable temperature. So that summarizes how to calculate the temperature of the Earth from the solar constant.